Hi, I'm Dr. Chris Delewa from the University of Manchester, and I'm going to give a simple overview of what chemical looping is and some of the ways it can help us achieve net zero. But first, we need to understand chemical looping. At its simplest, chemical looping is a way to split up a chemical reaction into sub-reactions using a chemical intermediate. For example, burning methane to generate heat. In a normal reactor, you'd react your methane with your oxygen, producing CO₂, steam, and generating that heat that we talked about earlier. In a chemical looping reactor, instead, we take that methane and we react it with a metal oxide, still producing our CO₂ and steam, and producing some metal. This process is essentially heat neutral, so we'll consider it as such for the rest of this video. We can then react that metal with oxygen, producing metal oxide ready to be used in the first reaction. And because in a chemical reaction, breaking a reaction down into several sub-reactions, as long as the reactants and products stay the same of the overall system, we produce the same amount of heat as we would have from a conventional reactor. It's this repeated reduction and then oxidation of the metal looping around the reactor that gives chemical looping its name. The metal is often referred to as an oxygen carrier because it carries the oxygen from the second reactor into the first reactor. Returning the system back to its initial conditions. The important takeaways from this are that because a chemical reaction enthalpy is conserved, if the overall reaction stays the same, we generate the same amount of heat whether we use a chemical looping reactor or a conventional reactor system. But because we don't mix gas streams, there are some entropy savings in a chemical looping reactor. These become most apparent when we compare more real-world reactors. Imagine we need to produce some heat, either for electricity generation or to drive some other chemical process on a plant. We might feed methane and oxygen into a reactor, producing CO₂ and steam, and generating the heat we need. But in a conventional methane reactor, we wouldn't be able to mix pure oxygen with the methane, both because that could cause a reactor to overheat, but more importantly, because separating oxygen out of air from nitrogen is prohibitively expensive. It's quite difficult to separate two gases from each other. So we end up using air, which means our reaction needs some nitrogen on both sides of these reactors. But if we're committed to fighting man-made climate change, this causes us a problem because we can't just let that CO₂ and nitrogen mixture go out into the atmosphere. And if we want to capture that CO₂, we'll need to separate it from the nitrogen if we want to be able to store it safely. This means once again we need some expensive gas phase separations to separate that CO₂ from that nitrogen. But in a chemical looping reactor, where our reaction is split into two parts, we'll react our methane with a metal oxide, producing CO₂, steam, and a reduced metal. That reduced metal can then be reacted with our oxygen-nitrogen mixture from the air, producing our metal oxide, ready for use again in the first reactor, and some nitrogen. Even after we've added that nitrogen to our second reaction, because we split it up, we don't end up mixing our CO₂ with the nitrogen. They both end up in separate sub-reactions, leaving different reactors. This makes the separation and capture of that CO₂ much easier, as separating the gaseous CO₂ from the solid metal and the easily condensable steam trivially easy. So to summarize, chemical looping is the splitting up of a reaction into several sub-reactions, normally through the use of an oxygen carrier. As it stops the reactants from mixing directly, a chemical looping reactor doesn't need expensive separation processes to capture carbon, making it an exciting alternative to normal reactors on the road to a carbon neutral society.